Okay, hello again. We're going to continue with Chapter 3, Section 2. And in this particular section, we're going to be focusing on what we call compound inequalities. Now, there are two types of compound inequalities that we have to take a look at. And they center on two different words. And those different words would be the and the or compound inequalities. And we're going to focus on initially what we consider the and compound inequalities. And there's two different types. Let's take a look at an example and see how we will solve them. Just like before when we were solving the inequalities, everything still comes into play in the sense that if you have to multiply or divide by a negative number, you must flip any inequality symbols. You will express your answer using interval notation once again. And just like before, you may recall that if it's less than or greater than that particular critical number, is not part of the solution, in which case we use a parenthesis. As with the infinity symbol, if infinity is involved, we will also use a parenthesis. If the critical number is part of our solution, then we have to use a bracket and a closed circle when it comes to the number line. Okay? But let's first of all take a look at an example of an and compound inequality. For example, let's say we have the following. Let's say we have a negative 6 is less than or equal to 2x plus 8, and 2x plus 8 is less than, let's say, the number 10. Now, once again, let me read this to you. And even though we don't see the word and in the problem, listen for it. This tells us that negative 6 is less than or equal to 2x plus 8, and 2x plus 8 is less than 10. And so what we want to do is try to get x alone in the middle. Right now we have three parts to this and compound inequality. Here's the first part, the second part in the middle, and the third part on the right side. And our goal is to get x alone in the middle. And so initially what we would like to do is to subtract 8 on all three parts. Okay? Here on the left side, negative 6 minus 8, that would give us a negative 14. We would have the 8 and the minus 8 cancel out, leaving us with a 2x in the middle. And now what we have here, 10 minus 8 is 2 on the right side. We didn't multiply or divide by any negative, so we are not going to flip the inequality symbols. Now, of course, once again, what we need to do is get x alone in the middle, which means I'm going to now divide all three parts by the number 2. Negative 14 divided by 2, of course, would give us a negative 7. 2 divided by 2 is simply x, and 2 divided by 2 would give us the number 1. And once again, we don't have to flip any inequality symbols. So once we have x alone in the middle, we have solved the inequality. But now we want to represent this on the number line. So let's draw our number line. I am going to represent the two critical numbers of negative 7 and a positive 1. Now, negative 7 is less than or equal to, so we will have to have a closed dot on the negative 7 because negative 7 is part of our solution. The second critical number of positive 1, since it's just less than, we're only going to have an open circle. Now, we are looking for the solutions that will make both these compound inequalities true. We need to find the values of x that are greater than the negative 7 and less than the number 1. And those values of x happen right here in between the two critical numbers. Any number in between negative 7 and 1 would make both of these inequalities true. Okay? And so now how would we represent this number line, this algebraic expression, using, of course, the interval notation? We start with the smaller quantity, -7. We go towards the larger quantity, the +1. And remember, we need to enclose these two numbers. And since -7 has a dot, we would use a bracket. The number 1 has an open circle, we would use a parenthesis. So our solution would be once again the range of numbers from -7 to 1. And once again, since -7 is part of the solution, we put the bracket. The number 1 is not part of the solution, so that's why we would use the parenthesis. Okay? When we talk about and, we are looking for the values of x that will satisfy both inequalities. And all of the numbers in between -7 and 1 will make both of these inequalities true. Okay? Let's take a look at another one, similar to this. Let's say we have -5 is less than or equal to 3x plus 4, and 3x plus 4 is less than or equal to a 19. Okay? Once again, we are looking to get x alone in the middle. This is an example of an and compound inequality. Once again, the word and isn't actually stated. We don't see it in the problem, but when we read it aloud, we interject that word and. Once again, -5 is less than or equal to 3x plus 4, and the 3x plus 4 is less than the 19. And so to get x alone in the middle, I begin by subtracting 4 on all parts. -5 minus the 4 would give us a -9, less than or equal to the 3x, and the 3x is less than or equal to the 15. Now to get x alone in the middle, we have to eliminate that coefficient of 3. So I'm going to divide all 3 parts by 3. Now here we have -9 divided by 3. That's a -6. Sorry, it's a -3. Less than or equal to 3 divided by 3 is just x. Less than or equal to 15 divided by 3, of course, is the number 5. Once again, to represent this on our number line, we would put the two critical numbers -3 and 5. -3 is part of the solution, so I fill in my circle. The number 5 is also part of our solution, so we would fill in our circle. Except we are looking for the values of x that will make both of these inequalities true. Where can we find such a value of x that it's greater than the -3 and less than the 5? That happens right here in between the two critical numbers. So if I was to represent this using the interval notation, we would be going from the smaller number -3 to the larger number of +5. And since both -3 and 5 are part of our solution, we would have to enclose them with brackets. Okay, so that would be your solution to that and compound inequality. Let's take a look at an and compound inequality where the word and is actually physically stated in the problem. For example, x plus 5 is going to be greater than or equal to 3, and 8x is less than or equal to 32. Now, let's just take a look at this one for a moment on why we have to throw the word and into the problem. Okay. In the previous two problems, we only had one algebraic expression. But here we could see in this example, we have two very different algebraic expressions. And when we have two very different algebraic expressions, we have to actually physically state the word and in the problem. Okay? So what we're going to do here is a little bit different. I'm going to solve them independently. I'm going to then graph them independently, and then I'm going to look to see what values of x these two inequalities have in common, okay? Now, in order for me to do that, it might be easier if I see them with different colors. So I'm going to do the first one in red. I'm going to start by subtracting 5 over. And that gives me x is greater than or equal to -2. So this solution here in red satisfies the first inequality. Let's take a look at this second inequality now. So for that, I'm going to use a different color. I'm going to go with green. To solve this one, I would have to divide both sides by 8. And if I divide both sides by 8, we get x is less than or equal to the number 4. Now we have solved each inequality separately, okay? And I did that because I had two different algebraic expressions. Now what I'm going to do is I'm going to graph each inequality independently. First, let me start with the red one, okay? So I'm going to draw a red number line. I'm going to put both critical numbers, -2, 4. Now once again, let's graph just the red inequality. We would have to do a closed circle on the -2, and we want to represent greater than -2, which is to the left, to the right of the -2. So here we have the red number line to represent the red portion of our inequality. But now I want to do the same thing with the green. So let me draw my green number line. Once again, I'm going to put on both critical numbers, -2 and 4. Now let's go and graph the green number line. I'm going to put a closed circle on the 4. And I need the values of x that are also less than 4, so I'm going to shade to the left. But now, remember, the original problem here is in black. So what I want to do is I want to now go to a single number line. I'm going to go back to the original color in black, and I am going to take the solutions that will satisfy both. I am looking to see where it has to be shaded in red and in green. If it's shaded in both colors, red and green, it will then appear on my final black number line. So let's do that. We have the two critical numbers, -2 and 4. Let's start with the -2. Is -2 shaded in red and shaded in green? Yes, it is. Here it's shaded in red, and here it's shaded in green, so -2 must get shaded in black because it satisfies both. Let's take a look at the number 4. Is 4 shaded in red and in green? Yes, it is. Since it's shaded in both red and green, we would shade it in black because the number 4 will satisfy both inequalities. Now let's take a look to the left of -2. To the left of -2, is it shaded in both red and green? And the answer is no. It is not shaded in red. It is only shaded in green, so we will not shade to the left of -2 in black. Let's take a look in between -2 and 4. In between -2 and 4, it's shaded in red and it's shaded in green, so we will have to shade it in black. Finally, let's take a look to the right of 4. To the right of 4 is only shaded in red. It is not shaded in green, so we cannot shade it in black. Remember, we can only shade it in the original color of black if it's shaded in both colors, red and green. So this number line represents the solution. Now we just need to represent it with the interval notation. Once again, we're going from -2 is the smaller to 4 the larger. Since both -2 and 4 are shaded in, we would have to use a bracket. And that would be your solution that represents this compound inequality. Okay? Let's try one more and compound inequality. Let's say we have 7x plus 2 is greater than 37 and 5 minus x is less than 6. Now once again, the word and has to be stated in this particular type of compound inequality, okay, because we have two very different algebraic expressions. And since we have two different algebraic expressions, I need to solve these independently and graph them independently. Once again, I'm going to use two different colors. Once again, I'll start off with red. Here for my first inequality, I'm going to start by subtracting 2 on both sides, giving me a 7x is greater than 35. Dividing both sides by the 7, we get x is greater than 5. So that is the solution to the first inequality. Now we have to go to the second inequality, and for that I'll go back to the color green. To solve this inequality, I'm going to start by subtracting 5 from both sides. That would give me a -1x is less than 1. Of course, I'd have to divide both sides by the -1. We will have an x on the left, a -1 on the right, but be careful. Remember, here I divided by a negative number, so I'm going to have to flip the inequality symbol. Now I have solved each part of this and compound inequality separately. I am now going to once again go and graph them on the number line independently. So first let's do the red number line. I put on both critical numbers. Here's -1, here's 5. Once again now 5 is not part of the solution, so I need an open circle. X has to be greater than 5, and that would be represented by the region to the right of 5. So here we have the red number line. Now I have to go and I want to graph the green number line. Once again, I put on both critical numbers. -1 is not part of our solution. Okay. Open circle there. X has to be greater than -1. We would shade to the right. But we don't care about just the red, nor do we care about just the green. Since we are talking about this and compound inequality, we are looking for the values that they have in common. Okay, so I'm going to go back to the original color, which was black. And so now I am looking to see what they have in common. We are looking to only shade in black that which satisfies both inequalities. So let me draw my black number line. Okay. If we were to take a look at these two number lines, where do we see that they are shaded in both red and green? Well, the only place that takes place is from 5 on up. Notice we are not including the number 5. Even though 5 is shaded in green, it is not shaded in red. It is not shaded in both colors. So we cannot include it in the solution. The only place where it is shaded in red and green is to the right of the number 5, which is this region right here. So we want to represent this region using the interval notation. We are going from 5 to infinity. We're going to have a parenthesis around the 5 as well as around the infinity symbol. and that would be your solution to that and compound inequality. Okay? So you have to be careful with the and compound inequalities. 99% of the time, okay, the solution is the region that falls in between the two critical numbers. Okay? But as we saw, that was true for the first one. Okay? Your first and compound inequality. It was true for the second and compound inequality. It was even true for the third and compound inequality. But once we saw this fourth one, this one was a little bit special, okay? We had to look very carefully at the two number lines, because remember, we are looking to see what number lines where it's shaded in both colors, okay? And that's why I use different colors, so this way you can see the difference between them. So that's the and compound inequality. Now let's take a look at the or compound inequalities. That's the second type of compound inequalities. Now the word or is always stated, okay? Unlike and. Sometimes the word and is inferred. Sometimes the word and is actually physically found in the problem. For example, let's say we have 6x plus 5 is less than or equal to -1, or x minus 3 is greater than or equal to 1. Now, once again, here, the word or is stated in the problem, okay? And we have two very different algebraic expressions. So I'm going to solve them independently. I will then graph them independently. Now, when it comes to the word or, we're not looking to see what satisfies both, okay? We are looking to take the solutions of the first one, the solutions of the second one, and as long as it's shaded somewhere, then it would appear on the final black number line. So, once again, let me go to red. Let me solve this first one by subtracting the 5 over. We get a 6x is less than or equal to -6. And when I divide both sides by 6, we would get x is less than or equal to -1. Okay, that takes care of the first solution. For our second solution, once again, I will go to the green. I'm going to add the 3 over, giving us now x is greater than or equal to the number 4. Okay, so now we have these two solutions. I am going to graph them now independently. Let's start with the red. I'm going to put on both critical numbers, -1 and 4. -1 is part of our solution. So I'm going to close in that dot. And I need the values of x that are less than -1. They occur here to the left. Next, we have to go and graph the green number line. Putting on both critical numbers, 4 is part of our solution. So we would put a dot. X has to be greater than 4. We would shade to the right. But now we want to answer the bigger question. The bigger question here in black is we are looking for the solutions to the first part or the solutions to the second part. So as long as it is shaded somewhere, we have to put it on the final number line. So here's -1 and 4. Let's start with the critical numbers. Is -1 shaded anywhere? Well, yes. It's shaded here in red. So I would fill in the dot. Let's take a look at the second critical number, 4. Is number 4 shaded in either color? It's shaded in green. So we would have to put it on the final number line. As long as it's shaded somewhere, we have to represent it on the final black number line. So to the left of -1 is shaded in red. So let's color it in. In between -1 and 4 is not shaded in red. It is not shaded in green. So since it's not shaded in either, it does not appear in black. To the right of 4 is only shaded in green, so we must put it on the final number line. Because as long as it's shaded somewhere, when it comes to the OR, color doesn't matter, okay? As long as it's shaded somewhere, it has to appear on the final number line. So now how can we represent this with the interval notation? Well, we're going to go from a negative infinity to -1 with a bracket, or bracket 4 to infinity. This is how we represent it using the interval notation. We take all of the first part or all of the second part and combine it on one number line and one interval notation. Let's take a look at another one. Let's say we have another OR compound inequality. X minus 5 is less than -2, or 4x plus 10 is greater than 6. Once again, two different algebraic expressions, so I am going to use, once again, two different colors. I'll start with red. Here, for the first part, I'm going to add the 5, and that would give us x is less than a positive 3. I now want to go and solve the second inequality, so let me get the green. I would subtract the 10 over, giving us 4x is greater than -4. And when we divide both sides by 4, we would get x is greater than -1. Okay, so we have solved each inequality separately. I'm going to now go and I'm going to graph them independently. So I start with the red. I'm going to put on both critical numbers, -1 and 3. Now let's start here with the red. 3 is not part of our solution. Open circle. X has to be less than 3. We shade to the left. So now we have our red number line. But now I need the green number line. Once again, I put on both critical numbers. -1 is not part of the solution. Open circle. X could be greater than the -1, so I'm going to shade to the right. Now, we don't want just the solutions of the red. We don't want just the solutions of the green. We know color doesn't matter when it comes to the OR compound inequality. And so we want to graph the black number line. And as long as it is shaded somewhere, either color, then we're going to put it on the black. So let's start with -1. Is -1 shaded in either color? It's shaded here in red. So we would put a dot. We would fill it in. The number 3, is that shaded in either color? Well, it's shaded in green. So we would fill it in. Next, let's take a look to the left of -1. Is to the left of -1 shaded in either color? Well, it's shaded in red. So let's shade it in black. Let's take a look in between -1 and 3. Is that region shaded in either color? Well, it happens to be shaded in red and green. So we would have to shade it in black as well. And then lastly, we want to take a look to the right of 3. To the right of 3, is that shaded in either color? Well, it happens to be shaded in green, so we must put it on the black number line. Now take a close look here. This particular black number line, we colored in everything. So what does that mean in terms of the interval notation that would represent the solution? Well, Basically, we are going from a negative infinity to infinity. Why is that? Because x, once again, is all real numbers. No matter what value I pick for x, it will make one or the other inequality true, okay? Because that's what we're looking for when you solve an or compound inequality, okay? So we've seen here with compound inequalities two very different words, the ands and the ors. Do be careful, okay? If you have, there are two different types of ands, okay? If you have just one algebraic expression in the middle, you could just get x alone in the middle, in which case your value of x will be those regions in between your critical numbers. If we have two very different algebraic expressions, the word and must be stated. And if the word and is stated, you want to solve them independently, you want to graph them independently, and then look to see what they have in common. What values of x will make both inequalities true? Versus the word or. Or is always stated in the problem. Or is also a little bit different, because when it comes to or, we don't care what color is, all right? As long as it's shaded somewhere on either number line, we have to put it on the final number line. Okay. That completes section 3.2 and the compound inequalities. As always, there's some homework problems for your pleasure. Give them a try and see how you make out. Please feel free to email me with any questions or concerns that you may have. Until the next time, be well.